Hi everyone. In the last few years, deep learning has been a growing technology across industries, right? It seems it's everywhere around us. And every new startup claims that it uses deep learning, right, as a means to raise more money. Now, when we first think about who is using deep learning, we naturally think about researchers and data scientists that work on high-level frameworks such as Python, PyTorch, and TensorFlow, and developing on Python. But when we think more truly who is developing the infrastructure, basically it's a low-level infrastructure that we need to develop in C, C++, and hardware. The problems in deep learning are very deep and difficult engineering issues that requires a lot of support, both for the training part, which is the part where you build the model, and for the deployment part where we run the inference. In this lecture, we'll understand what are the problems and how oneDnn solves some of them. Okay, so first let me provide a short intro about myself. So my name is Anat Heilper, and I'm an AI architect at Intel Co-Architecture Group. I am software architect lead. I've led several deep learning accelerator projects, both in inference and training. We'll cover in more depth what it means in the lecture. And I have vast experience in deep learning for 2014, and on optimization of software stack vertically from the framework level to the low-level building blocks. Okay, so what we will cover in this lecture. First, we'll have a short introduction to deep learning. It's not, no mathematical background is needed, just to have a common ground on the terminology. Then we will understand what is the software deep learning, what is the challenges that involves providing software for deep learning. Then we will hear what is oneAPI. I know that Guy mentioned it a bit in the previous lecture, but we'll see what is the ecosystem, what is the vision that Intel tries to solve. And then we'll see what is oneDnn and architecture and design in oneDnn. Okay, so introduction to deep learning. First, let's understand where it began and started from. So it started from artificial intelligence. In artificial intelligence, we basically mean everything that computer does that used to be considered as human doing. For example, navigation, recommendation, understanding of language, and so on. From that field arose machine learning, which means that computers are able to learn from data by algorithms that are not explicitly written by humans. For example, face detection, by identifying specific features in images. The subfield of deep learning is using and mimicking how the human brain works in order to understand more complex structures in data. And the field of deep learning really started to kick off in 2012 after it won in a very important competition called ImageNet and overcome classical machine learning algorithms. Okay, so how does the neural network look like? As you can see, it's basically a computation graph that consists of nodes, which we call neurons, and edges. The convenient way to visualize the neural network is as seen here with the vertical, that nodes are arranged in layers. Each layer is divided by a vertical line. And when we have more than one internal layer, it's called a deep neural network. Okay, so this is what deep means. On each node, we have weights. And if nodes are connected to another neuron, then there's a signal that is passing and a computation that is done from neuron to neuron. Just by looking at this picture as infrastructure level, we can understand that there's a lot of parallelisms that can be done in the computation. Okay, because neurons in the same layer would perform the same computation, so we can do it in parallel manner. In addition to that, I've shown here a very small graph. Okay, we have a total of less than 10 neurons in this graph. But in real life examples, we have a lot of neurons, which means that we need a lot of capacity to hold the neurons, and also so the computation increases and the data capacity that we need increases as well. Okay, so now let's look at deep neural network problem from two perspectives. One as a data scientist, and then from the software perspective. Let's say that now I'm not a software architect, I'm a data scientist, and I want to build a classification network to classify images. Our most common workload neural network to do that is called the CNN, Convolutional Neural Network. To do that, my mission is to be able to build a graph that will allow me to classify between images in the most accurate manner. Okay? So let's see how this is done. First, I need to train the model. Train the model means that I run the network through many labeled data. In this example, for example, I need to want to build a classification to identify 3 classes, bird, bicycle, and strawberry. I will have a lot of labeled data. On each image, I will annotate it with what image I have, and then I will run it through the network. In the example here, the network has made an error. Instead of bicycle, it guessed strawberry. In order during the training process, the network is learning the correct weights, such that in the next time it will see a bicycle, there will be greater chances that it will guess it correctly. This process is iterative, so again, it's very compute intense and also data intense because I need to pass it through many images. But at the end, hopefully, the data scientists will do it work correctly, and the process would converge. When the model is ready, the weights are ready, and then we can deploy the model. The deployment is done, is called the inference. Okay, this is what is done when we search for cute cat images in Google, or ask for a recommendation system to choose a movie. Okay, we basically run an inference query. Okay, now as you can see here, it looks as if the training and inference process, at least in the forward pass, are very similar, but there's different compute needs between the training and inference. And we'll cover it in the software part. Okay, so we finished with some introduction to deep learning. We know what is training and inference. We know that we have neurons. We have some of computation that needs to be done. Let's see what we need in order to implement in the software. Okay. So now I've said, and let's look at the same problem now from the software perspective. From the software perspective, basically, I don't care what is this neural network. I know that I have a lot of computation that needs to be done on a lot of data, and my mission is supposed to be functional correct, to have the correct result, and that it will be performant. Now let's look what this means in the field of deep learning. So as I told you before, we have the training process, which is iterative manner. I need to run it through many images. So if I want the software to be efficient, the optimization that I need to do here is throughput. Okay, I need to be able to run it in a distributed manner. If I can, because the problem is highly parallelized, I will run it on many machines. It can be Intel, it would be nice, but if not on GPUs or any other accelerators that are available. And I will distribute the compute, and I need to be able to manage this software to share the data between the different machines until it converges. Because we see that we need also to do correction of the networks towards the computation, all of those computation in the training process are very sensitive to numerical errors. So the computation has to be done in highly precision, which means 32 floating points, and to be sure that we don't miss any value within it. Now the training is done, as we said before. I want to deploy it. When we run inference, for example, when we want to search for images on the web, we want it to be done as soon as possible. So the optimization that I want to do here is on latency. okay? Especially in real-time application. We may prefer to do something faster than accurate, right? Otherwise it won't be relevant for what we want to do in our daily life. So in inference, the optimization is on latency, and that is a lot of software optimizations and algorithms that are done in order to lower the precision from 32-bit floating point to 60-bit, 8-bit, or even lower precision. So although the problems looks very similar between the training process of the workload to the deployment on inference, from the software perspective, those problems are very different. And also engineering-wise, this is why we have even different hardware accelerators for the training process and the inference process, because the optimization problem is completely different. And this is what we need to solve in the infrastructure level. Okay. Another challenge that we have from the software is that the deep learning models are exploding. Guy in the previous lecture mentioned it for a second, but in deep learning, the sizes are keep getting bigger and bigger because it has been shown that the bigger the models are, bigger, I mean, the capacity of the weights that we've shown in this simple graph that I've shown before. The bigger the model is, then the more accurate it is. In the graph here, you can see an example of, sorry, I need to be here. The size of the language model, which means that models that have to do with language translation or understanding, they're just getting bigger. And GPT-3, there at the end, the size of the model is 650 gigabytes. And this is the size in the inference stage. In the training, it takes much more memory capacity just to make the model converge. Okay, so, okay, let's say that this is a number and maybe it would even be bigger. So what? Why do we care about that? We care about that because the larger the model is, first we need more capacity, right? It costs us more money for the storage. It means that from an optimization perspective, it won't be on our cache, right? No, we need to understand how to make our algorithms be more efficient. It means that it requires more power, then we need more infrastructure from the power perspective, both in the data centers and on deployment. And it will take more time. It will take more time to generate models, both in the training time and in inference time. And this means that many applications won't be able to use those sophisticated deep learning models because they're not relevant for real time. So basically, we care because time is money, and we need to see how we can optimize it. Last thing I want to show with regard to software is to show how it looks on the low-level details. The example here is one of the most common layers in the deep learning, which is convolution layer, which is simply a matrix multiplication that is done in high dimension. Okay, this is pseudocode, and now I don't want us to get to every bit here, just to think what it means to implement it on every different hardware. Okay, so we have many nested loops, and in matrix multiplication we can have several optimization opportunities of what data we keep in memory and what we need to fetch from the further levels of memory. And this is very hardware dependent, okay? Depends on the cache line size that we have, on the vector size that we have, and the registers. So on each different hardware, we would implement that differently in order to have the best performance. Which means that at the end that someone needs to program it, and it will be in the low level of C++. Great. So because of lack of time, I will go over what is oneAPI very shortly, and then we'll go to oneDnn. So again, we need, in our daily life, deep learning runs on every one of those devices, right? It's everywhere we want to use it because it gives us better precision. And then at the end, it means that for every such device, we will have different code, even if it's for the same problem that we want to solve. which means that it's a lot of burden for us, for the developer, to do that. And now the question is, can we do it simpler? Too complicated, we know how to do that, right? We have different code base for every one of those devices, different tool chains, logs, traces, debug, much of fun. So the vision that Intel has is this oneAPI initiative, which means to be open source, multi-architecture, multi-vendor. This is something that Intel started, but every vendor can join it, and we can, as a community, contribute to the spec and to the libraries. I won't go over that again because Guy already shown it. We have vertical support to different vendors and through the oneAPI. Guy mentioned one library out of the spec, which is oneDPL. I will talk about oneDnn out of the spec, which is a deep neural network library. Okay, so back to the AI domain. As I mentioned, we think of the deep learning researchers and scientists, which usually go to the PyTorch and TensorFlow, right? But the low-level infrastructure is done beneath as a backend. In here, it's the example of Intel's implementation on how this vertical software stack looks like. So in addition to the development on the frameworks, we have a lot of tools that we need to make this ecosystem work on how to deploy the neural networks and how to optimize them. Okay, so after we've talked about deep learning, the software, and oneAPI, let's see what is the oneDnn library looks like. Okay, so oneDnn is the implementation of the building blocks that we need for deep learning for various architectures. This oneDnn is open source and it's continuously evolving, and many applications are already using oneDnn. It's already a default backend for the CPU on TensorFlow and PyTorch and OpenVINO. Okay, so what is the programming model of oneDnn? It has the following design points that, again, every architecture can use it, and once you implement the primitives, you can enjoy the whole ecosystem of oneAPI, not necessarily for Intel. So we start with primitives. The primitives are the functions that we need for the deep learning: convolution, pooling, ReLU, and many other layers that are needed for deep learning. The primitives have a state part that is immutable. This is the tensor parameters, the sizes, dimensions, the data types, and the mutable part that is used for the storage during the computation. For a primitive, we commonly have a post-op, which means that because there's a pattern in the graph, a lot of operations often go together. And then if we know this pattern in advance, then we can utilize it and optimize the operations through a software pipeline, better memory management, and other optimizations that can be relevant to the specific operation. In addition to primitives, there is the engine itself, okay, on what engine we want to run, what's the CPU, GPU, FPGA, and so on. When we define a computation graph, let's say now I have a computation graph, I define it on which stream to run, and then I bind it to an engine. And in addition to that, we have also memory objects that encapsulate the handle to the memory that of the device that we run at. Okay, so now let's look at an example. Let's say that I want to build now a really simple neural network that consists of two operations. First, I need the memory objects, right? I need an input, output, and usually in neural network, as I have shown in the beginning of the lecture, I need weights. Now I define the operation that I want to run. And as I said, we usually have like a post operation that goes right after the main operation. Like after convolution, I'm doing some nonlinear function. So that would be defined as a post operation. After I define my computation graph, I define on what stream I'm running. and then I bind it to an engine. After I have all of this information, then I can generate the code to the specific problems that I want to run. The code is generated in a just-in-time manner, which means that the code can be optimized to the specific problems that I want to run, which is, if you think of it conceptually, you can write much more efficient code if you know the exact dimensions of the problems that you want to solve. Okay, now let's look at a code example of a really simple function, which is called a ReLU. Okay, as you can see, the definition is for any value that is lower than 0, it will be 0. Otherwise, it will be x. And this is the computation graph that I want to build. Okay, we have operation, stream, memory objects, and engine. So how does it look like in oneDnn code? I have the DNN namespace, and I define the engine and the stream. Now, I need to define the memory objects. For example, the input. As you can see, the input is multi-dimensional. This is the NCHW, this is a common memory format. What data type I need to use, which is a floating point 32. And now I define, after I define the memory object, I have the object itself in the source memory. And now I write the object, I copy the input to the memory of itself, to the memory object. Okay. Now I define the operation that I want to run it. Okay? I want to use ReLU as a forward pass of inference, and the other parameters that are required for ReLU. And define the descriptor. And now I have the code generation itself. And I want to relate to the comment. This is the point where we do the code generation. Now, on one hand, you can say that this is very inefficient. Why do I compile the code just in time and not have a compiled like we write usually code, right? So the reason for that is portability. Okay, because we remain in this higher level of abstraction, that it's much more easier to port the code between engines, and all the gory details of the hardware implementation is the headache of the library maintainers, and not of us, of the programmers, in that level. Okay, so now I have the execute of the kernel. I want to show you one more thing, that in fact only in this level, in this line, I bind it to an engine. So I can define a computation graph in abstraction level and only bind it to a specific engine in a much later time. So this also helps us in abstraction of the computation graph. Okay, so I've defined the graph, and now I can execute. And because I have by sending the stream with the input and output, and now I wait for the execution to wait. And then if I want, I can even read the data from the device and continue with my application. Keep in mind that in real life applications, it does not end with the neural network. We have other stuff that we need to do. So it's very convenient to do that as we remain in our C++ level. As I mentioned before, many applications are already using oneDnn, and we are not aware of that. Okay, all of the headache of the low-level data are abstracted away from us. It's a backend for PyTorch, TensorFlow, Onyx, OpenVINO, and many others will support it as well. If you want to have more information about it, then again, you can see also the YouTube channel of Guy Tamir. There's a GitHub of oneDnn and the oneAPI spec that you can see, and also contribute if you want. Thank you. If you have questions. Question? Yeah.
So does the code generation have anything to do with the compilers in C++, or is it all just like machine code?
So
the actual optimization of the low-level engine.
So the actual optimizations, it's done inside the library. Okay. Now in deep learning, you have lots of ways to optimize. Currently, the optimization is done on the kernel level, that you just do lowering of the code until you get to the assembly. But there's also very good practice of doing graph compilation when you have a lot of layers to do together. Currently, it's in oneDnn, it's still in alpha, and it should be released in 1 year also a graph level compiler. But there are also tools of Intel that does the graph level optimizations. Okay, thank you.